Hello everyone, I'm Abdullah Salman from Group 2, and today we're going to talk about the amplitude modulation. So first of all, let's start with an introduction. What's modulation? Modulation is a message itself, is a signal. Example as the audio signal, a signal transformation to format suitable for transition through or chosen medium, often involve other signal such as carrier signal. The message modulates the carrier to produce the transmitted signal. Modulation types, we have the continuous wave modulation and we have the pulse modulation. For the continuous, we have the carrier. The carrier is a sinusoid, and for the pulse, the carrier is a pulse train. For the continuous, it's a traditional mode. However, for the pulse, it allows for digital communication. Benefits of modulation. Benefits of modulation. Modulation can shift the spectral content of a message signal into a band which is better suited to the channel. It has another benefit, which is modulation permits the use of multiplexing, and modulation can provide some control over noise interference. Objective is we are going to learn about the modulation and the modulation techniques and the AM generation and detection. Some variant, we have the double side band full carrier, two side band and a carrier. We have the double side band suppressed carrier. We have the single side band. We have the single side band suppressed carrier and the vestigial side band. So we start with the first one. Baseband is a range of frequency signal to be transmitted. Passband communication, transition without frequency shifting. Carrier communication, use modulation technique to shift the frequency. Okay, so first of all, we're gonna start with the DSB-FC, full amplitude modulation. AM modulation is a fundamental modulating process in communication system. The carrier frequency signal must be bigger than the modulated signal. As you can see here, FC must be greater than FM. Modulated is used to generate AM signal. As you can see here, the block diagram, we have first of all the modulating signal, then it goes to AM modulator, and the carrier signal also enters the AM modulator and comes out with this equation, which is the formula of the DSB-FC, which is equal EC plus VMT cos omega CT. We use DSB-SC to increase transmitter efficiency. The carrier can be removed, suppressed from the AM signal. This produces a reduced carrier transition or double-side band suppressed carrier signal. And here is the block diagram. VMT enters the DSB-SC modulator with the VC and come out with this equation. So now we go to the single side band suppressed carrier. We have this block diagram, which is basically a VMT with a VCT enters the modulator SSB single side band and come out with this equation. We have this equation, which is half VMT cos omega CT plus minus half VMT sine omega CT. Then later we go to the generation part. We have direct method and indirect method. We start with the direct method using a balanced modulator. This is this message signal and this is the carrier signal. They come out after modulation and multiplication. It will be this is the output of the system. Indirect method uses two full AM modulator. The input signal are the same with different polarity. So we have so we divide the amplitude of each one of them by two. Have negative half and positive half. Full AM modulator comes with the full AM modulator, and after summation and subtraction, it will come with this equation. AM SSB-SC generation can be realized in two steps: generate first signal and then filter the signal. As you can see here, the block diagram, we have a passband filter, and with the output of VSSBCS. So we now go to the super heterodyne receiver. We have the antenna, we have the RF tuner, then it goes to the RF amplifier, to the mixer, to the IF filter, to the IF amplifier, to the envelope detector, and then to the speaker, which is the output. And of course, we have some like the oscillator, we have the common tuning, and this formula, which is the IF. Then we go to the advantages of this system or this receiver. We overcome weakness in some components that could not operate at higher frequency. Component can operate at fixed frequency, which will optimize its usage and reduce cost. Thank you.
Bismillahirrahmanirrahim. My name is Yahya Muhammad Sinjab, and today I will be explaining our third chapter in our syllabus, which is the angle modulation, and we are group 2. And now let's start with the introduction. Besides the AM technique, other well-known modulation techniques is known as angle modulation. Previously we talked about amplitude modulation, and now we will be talking about angle modulation. Angle modulation, or exponential modulation, which is another name, uses modulating signal to change frequency and phase of the carrier signal. So our focus is on the carrier signal, and the general expression is ST equal to A as an amplitude cosine theta t. Therefore, we can change the amplitude and angle of the carrier signal in order to send information signal. So, as a purpose of sending the information signal, we can manipulate the angle and the amplitude based on our target or our goal. And now, let's talk about the angle modulation. Information signal, which represents VMT, can be transmitted with the amplitude of the carrier signal, is held constant, and the angle, either the phase or frequency of the carrier, is varied linearly with the information signal VMT. And we have to notice that it's mentioned that it varies linearly. And if carrier signal, let's say, is VCT equal to EC cosine omega CT plus phi CT, and this instantaneous angle value is theta CT equal to omega CT plus phi CT, therefore the instantaneous angular frequency and instantaneous angle value are given by omega I equal to d theta CT over dt equal to omega C plus phi dot, which is phi derivative CT, and theta CT equal to the integration from a range of 0 to t of omega I dt equal to omega CT plus phi CT. And to keep the time, I will not read the equations anymore, I will just show the equation. And now let's talk about the phase modulation. Phase modulation, which has a symbol of PM, represented by PM as a shortcut. It implies that the phase deviation of the carrier is proportional to the modulating signal VMT, where, and if we look at the equation, Kp is the phase deviation constant in either radian over volt. Therefore, VPMT equal to EC cosine omega CT plus Kp VMT. And now let's talk about frequency modulation. FM implies that the frequency deviation of the carrier is proportional to the modulating signal. Notice that at the beginning, in the phase modulation, the phase deviation of the carrier is proportional to the modulating signal. However, in the frequency deviation is proportional. And the equation has been shown here, where Kf is the frequency deviation constant in radius or second or volt, over second over volt. Integrate, after we do the integration, therefore the FM signal will lastly equal to the last equation shown in the photo. And now let's talk about frequency spectrum of FM signal. The number of sidebands depend on the value of beta. So we have to notice that beta is very important here. And now let's talk about two rules. First rule is the Carson rule, and then we will be talk about the narrowband FM, the power FM signal, and the generation, and so on. Talking about the Carson rule, it's shown that errors due to the band limited signal of FM can be neglected if 98% of the power of the signal has been transmitted. So if 97, 96 or less, Carson rules cannot be applied, or the limited signal band, the band limited signal cannot be neglected. Based on Bessel function, 98% of signal power has been transmitted if the number of the sidebands transmitted equal to beta plus 1. So we have a case where we can know that 98% of the signal has been transmitted, which is when the sidebands, the number of the sidebands transmitted equal to beta plus 1. Therefore, the bandwidth needed for the FM will be at the given equation. And now let's talk about the NB-FM. For FM signal with the small index modulation, if beta less than 0.2, it's called narrowband FM. And for FM signal, we have said previously as known, we can show the equation here. And then when let's say that theta t equal to beta sine omega mt, hence the equation will be represented as follow. And now let's talk about the power in FM signal. Power signal depends on amplitudes and not on the frequency. This is a very important note to highlight. The power signal doesn't depend on the frequency, but it depends on the amplitude. So there is a relationship between the amplitude and the frequency here. And the power signal here. The amplitude of FM signal constant. Therefore, power transmitted depends on only the amplitudes of the signal, and it doesn't depend on the modulation index. Means it doesn't depend on the frequency, neither it does with the beta. For AM signal, the power transmitted depends on the modulation index. It can be seen from Bessel equation as shown at the figures, and in other words, the total power of FM signal consists of power carrier component and all power inside band. So when we want to take or want to find the total power, we need to consider the power in the carrier and the power in every side band. And now let's talk about the generation of FM. There are two techniques, as usually, direct and indirect. For the direct, for example, the varactor diode, reactance modulation, voltage controlled oscillator, and another very important way, which is the cross-buy FM generator. Frequency modulation using these techniques do not have the mechanism to prevent frequency drift, which in another word it means it is not stable. And the crystal oscillator is stable but has a high Q. Frequency cannot be changed directly. So, as a result, to address this issue, the cross-buy modulator was developed. The cross-buy circuit incorporates an automatic frequency control, and it is represented by the direct method. The basic concept: maximum deviation of 5 kHz of direct methods, including cross-buy, are unstable for WBFM. To overcome, so we have an issue and we have a solution. The solution: frequency multiplication is used. Why? To manipulate the value of the frequency. Frequency deviation. We have frequency, deviation, modulation index are multiplied. Modulating signal frequency unchanged. So we have to make sure to understand that the modulating signal is not affected by this multiplication, as shown in the figure, where the input signal going to the reactance modulator and going out to the antenna. And the figure at the bottom showed the discriminator, the mixer, the crystal oscillator, and so on. And now let's talk about the indirect method, which is our focus here, which is the Armstrong method. While it is not possible to directly vary the frequency of the oscillator, the crystal oscillator, it is possible to directly vary its phase. So we cannot change the frequency, so let's change the phase. Use PM to generate FM signal. PM using the integral of input signal is FM. The carrier source is a crystal, so carrier frequency stability is high because of the crystal, because it's stable. So no need an AFC loop. However, deviation using Armstrong method is small, maximum only 25 Hz lower than direct FM, which means it is not sufficient for wide band to be used as wide band. Use of only multipliers is inadequate and has to combine with mixers. So since we have this issue, as a result, using multipliers isn't enough. We have to use mixers. Okay. Armstrong method is elaborated here in the figure, and FM amplitude of the modulated carrier is held constant, and the time derivative of the carrier's phase is varied linearly with the information signal. And now let's talk about the general equation, which is as shown: EC cosine omega CT plus phi CT. And for narrowband FM, phi CT, when it is less than 1, therefore cosine phi CT almost equal to 1. And sine phi CT equal to phi CT. Therefore, the equation will be as follows. And now let's talk about the generation of WBFM. The instantaneous value of the carrier frequency is increased by n time, which is the multiplier, because we will manipulate the value. So the equations will be as follows. The omega I equal to omega C1 equal to omega C plus phi CT derivative. And omega 2 will be shown as follows. And now there is a very important point, which is the comparison between the FM and AM, as shown here in the schedule or the table, in the table. And now let's talk about demodulation of FM signal. Demodulation process is done in order to recover back or to get back the information signal transmitted. So we transmitted the information signal, but we want it back, so it is all the way around. And the basic concept of it is circuit to detect the frequency variation. Two techniques can be used, direct or indirect. Indirect, we talk about the phase lock loop. Direct, we talk about discriminator envelope detector. So from FM to AM, using the discriminator, this technique is required to convert FM signal to AM signal, and then by using AM modulation circuit is to get back the information signal. So FM to AM, using modulation circuit, AM modulation circuit, get back the information signal. This technique, FM to AM, is called slope detection or discriminator. Block diagram of the detect circuit as shown below. And now talking about the mathematical analysis, we can see the FM equation, differentiated yields. After the differentiation from the above equation, it can be seen that the amplitude of the signal contains the information signal. So the amplitude of the signal is an envelope of the signal, and the equation is given by EC equal to omega C, EC multiplied by omega C plus KF VMT. And these are the remaining of the equations to be clear how these questions can be solved. And now let's talk about for effective detection. Well, for the effective detection, the constant amplitude of the FM signal is required. Therefore, an amplitude limiter is used. Below is a block diagram to elaborate that. And a limiter will limit the output from to 1 or negative 1, depends on a positive or a negative cycle. Positive 1, negative cycle, negative 1 of the FM signal, and ECT larger or equal to 0. And now let's talk about the output of the limiter is a square wave. So, as shown in the below, it will be a square wave, and as a square wave we use Fourier series equation for square wave as usually, and this was taught and explained in Signal and Systems last year. For FM signal, the angle varied in accordance to the amplitude of the information signal, as shown in the equation. Therefore, the limiter output is a function of theta t, and the equation can be written as shown in the equation in the slides. And then we have the output of the limiter, explained clearly and step by step mathematically here, and the output of the bandpass filter will be E naught t equal to 4 over pi cosine omega c t plus kf integration of vmt dt. And then we have the analysis, the slope detection as shown in the block diagram, then explained briefly in the equations, ending up with the equation that says yt equal to 4 over pi vl omega c plus 4 pi over vl kf vmt, where the first part represents the DC and second part represents the AC, which indicates that the output consists of DC voltage plus AC voltage, which is proportional to the modulation of the FM signal. Normally, DC voltage doesn't appear on the output. A capacitor can be applied in series with the output to remove the DC voltage, as it was explained in electronic circuit design. And now let's talk about the PLL indirect method as shown in the block diagram. The in, which is the input, will go to the mixer and then going to the low pass filter, then to the V out, and we have a voltage controlled oscillator connected to the mixer. And straightforward operation, the PLL is looked to the FC, and any deviation from FC will produce a voltage in proportion to Vm. The input is FM signal, which is shown in the equation equal to EC cosine omega CT plus KF integration of VMT dt. And now lastly, let's talk about the pre-emphasis and de-emphasis. Pre-emphasizing is the audio for an FM signal is effective because the noise output from an FM system is proportional to an audio frequency. Furthermore, the level of high frequency sounds is usually less than the lower frequency, and to prevent this, transmitter must increase the level or gain of the higher frequency to compensate. Now let's talk about the pre-emphasis. Pre-emphasis, the higher frequencies are increased in amplitude before being used to modulate the carrier, and therefore will be less affected to noise. De-emphasis, it is the mirror of the pre-emphasis process, so it is the opposite. As shown in the figures, it explains in detail the details and the way we can deal with the pre-emphasis and de-emphasis. And now let's talk about why FM stereo. The FM super heterodyne receiver shown in monophonic. Stereophonic FM was proposed to make system more natural. Music or sounds can be affected by space, instruments, and so on. Stereo, however, allows reproduction of sound with unique directivity and spatial dimension. So it allows us to have something more natural, since the sound or the audio can be easily affected. So the sound from left side reproduced by left speaker L, and vice versa. It is very important that stereo broadcast should be compatible with mono receivers. Existing mono should be able to retain the monographic quality it will receive, L plus R, channel bandwidth L plus R equal to 200 kilohertz, and delta F equal to 75 kilohertz. And noise in reception, in FM reception, as shown here in the block diagram, the XFM T plus N T will be going to the band pass filter, then going to the amplitude limiter, discriminator, and lastly to the low pass filter. And as it's shown here in the photo, it describes and shows in detail how the mathematical information related to this part. That's all for today. Thank you very much for listening. Have a good day.
Now we are going to talk about radio digital modulation. Did you know pulse signals from the previous modulation or coding method normally are not transmitted in their original form? They will modulate a carrier that is suitable with channels used. Digital signal can also be transmitted through free space if analog carrier signal is used. Okay, so this is what we are going to learn. First, ASK, second, FSK, and PSK. Next slide will explain it more detail. This modulation technique is similar to the analog modulation, in which the modulating signal will vary the amplitude, frequency, or phase of the carrier signal. The only difference is that the modulating signal is digital. There are three techniques that can be used, like what I said: ASK, amplitude shift key, FSK, frequency shift key, and PSK, phase shift key. Okay, the first one we are going to talk about ASK, amplitude shift keying. Okay, this is the analog signals which convert it into the digital signal. This signal we times with this, and then the output will look like this. This one is used to switch the carrier amplitude low and high. Also, this one is called on-off keying, OOK, and interrupted continuous wave. The string of pulses from the digital signal will change the amplitude of the carrier signal. This is the circuit for ASK generation or transmission. First, they will use using multiplier, or they can use using on and off switch. Second is ASK receiver using envelope detector. The second one, or they can use using coherent detector. We are going to talk about frequency shift keying as FSK. For your information, FSK is by adding 2 ASK. This times 2, this one, and times another ASK here. So the output will be like this. It will be doubled. The generation of an FSK waveform at the transmitter can be achieved by generating 2 ASK waveforms and adding them together with a summing amplifier. This is what I said just now. They will add 2 ASK here, and then we'll use a summing amplifier here that will make it this output. For FSK generation or transmission, they use three methods. At first, it's using the multiplier. Second, by using switch, and third is by using VCO. VCO is meaning voltage controlled oscillator. For FSK receiver, there are two types, asynchronous and synchronous. This here we can see the difference between these two images. And on the left is asynchronous. They have two filters here, and then it combines by using logic comparator. On the right is synchronous. We have two mixer and we have an amplifier, and we filter it by using low pass filter. Lastly, we are going to talk about PSK, phase shift keying. PSK is different from ASK and FSK. The analog signal originally looked like this, times the bipolar, and the output will look like this. The phase of the carrier is set to 0 degree or 180 degree depending on the digital signal. For the PSK generation, it will only use multiplier. By filtered it first using LPF, then mixer that times with the carrier oscillator, and we will get the PSK. Next is the PSK receiver. It also uses a multiplier. PSK demulator must use coherent detector. The advantages of PSK are immune to noise, the same bandwidth with ASK, and it is multi-level. This is the summary of the radio digital communication. When the ASK, the analog signal, when it times with bipolar, it will look like this. Amplitude, the clue word is amplitude. So when it is 0, the amplitude will also be 0. There are no amplitude seen on the signal. For FSK, the frequency will be changed. When it is 1, the frequency will be higher. When it is 0, the frequency will be lower. Lastly, for PSK phase shift keying, so which means the phase will be changed. When the transition from 1 to 0, it will change from 180 and it change from 0 degree. It will continuously change the phase until we see another transition. The advantage or disadvantage for ASK is more noisy, but the bandwidth is efficiency. For frequency shift keying, it is less noise with a larger bandwidth. For PSK phase shift keying, it has less noise than ASK and FSK, but similar bandwidth to ASK. At the bottom is how we calculate the bandwidth for the third harmonic and fifth harmonic. That's all from me. Thank you.